2 trillion. 2 trillion galaxies. But there's no rush in this video. Nothing you need to memorize, no conclusions you need to reach by the end. Just a careful look at one of the largest ideas that modern science has ever tried to pin down. We're gonna take our time because the subject demands it. Not with speculation or spectacle, but with what we actually know, how we know it, and where the limits are. We're exploring a number that sounds abstract until you understand what it truly represents. 2 trillion galaxies in the observable universe. Not a guess, but a carefully constructed estimate built on a century of patient work. This number is more than a statistic. It's a key to understanding the architecture of everything we can see. To grasp what this means, we need to start with what a galaxy actually is. At its simplest, a galaxy is a collection of stars, gas, dust, and dark matter bound together by gravity. But this definition hides staggering variety. Our own Milky Way contains between 100 and 400 billion stars. We don't have an exact count because many are hidden from us. We are inside it, trying to map a forest while standing among the trees. But the Milky Way is just one type, one form in an incredible diversity of galactic architecture. Some galaxies are unimaginably larger. The supergiant elliptical IC 1101 spans hundreds of thousands of light years and may contain 100 trillion stars. On the opposite end live dwarf galaxies like Segue 2, a faint satellite of the Milky Way containing only about 1,000 stars. Most galaxies in the universe are of this modest variety. Not the grand spirals we see in photographs, but small, dim, collections barely visible to our instruments. This range in size and brightness is the first reason counting galaxies proves so difficult. Where do you draw the line? Is a dense sphere of stars a small galaxy or a large star cluster? What about ultra-diffuse galaxies, which can be as wide as the Milky Way, but contain so few stars that they're nearly transparent? The figure of 2 trillion includes countless objects on these boundaries, an estimate built on judgment calls and careful reasoning. For a long time, the accepted estimate was different. For decades, astronomers spoke of 100 to 200 billion galaxies. That number was grounded in one of the most significant experiments in modern astronomy. In late 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of the sky, a region so small it would be like looking at the eye of a figure on a dime held at arm's length. They gathered light for 10 consecutive days. Many thought it was a waste of precious telescope time, but the resulting image was not black. it was speckled with thousands of faint smudges, each one a galaxy. This was the Hubble Deep Field, and it changed everything. In that minuscule fraction of the sky, they found about 3,000 galaxies. Extrapolating that density across the entire sky led to the estimate of roughly 100 billion galaxies in the observable universe. But there was a problem with that number. It was based only on galaxies bright enough for Hubble to see, like trying to estimate the population of an ocean by only counting the large fish caught in a net. In 2016, a team led by Christopher Consolis at the University of Nottingham realized this limitation. They analyzed not just what we could see, but how galaxies change over time. Because a light takes time to travel. Looking farther out means looking back in time. Consolis's team studied how the number of galaxies in a given volume of space changes across different cosmic epochs. They found that the early universe was far more crowded with small, faint galaxies. Over billions of years, gravity pulled these small galaxies together, merging them into the larger systems we see today. The Milky Way itself is the product of many such mergers, a tapestry woven from smaller threads that once were separated galaxies. The implication was clear. To account for all the small, early galaxies that must have existed to build the galaxies we see now, the total number had to be far higher. Their mathematical models suggested the observable universe contains about 2 trillion galaxies. About 90% of them are too faint, too small, or too distant for our current telescopes to detect. The earlier estimate had missed the majority. This leads us to a critical phrase, the observable universe. This is not the whole universe. It's only the part from which light has had time to reach us since the beginning of everything, about 13.8 billion years ago. Because the universe is expanding, the most distant light we can see comes from objects that are now about 46.5 billion light years away from us in each direction. That defines a sphere with a diameter of about 93 billion light years. Everything within that sphere is our observable universe. Everything beyond it remains forever hidden from our view. What lies beyond that horizon? We do not know. And by the laws of physics as we understand them, we can never know. The light from those regions has not had enough time to reach us. Most cosmological models suggest the full universe is vastly larger, perhaps even infinite. If it is uniform, then the total number of galaxies is not 2 trillion, but unimaginably larger, perhaps infinite itself. 2 trillion is merely what we can see or infer from our small vantage point in space and time. These galaxies are not scattered randomly across the void. They are arranged in an immense, delicate structure we call the cosmic web. Picture the universe not as a starry blanket, but as a sponge or a network of neurons. Galaxies line up along filaments, great rivers of dark matter and gas that can stretch for hundreds of millions of light years. Where these filaments intersect, you find dense knots, galaxy clusters containing thousands of galaxies bound by their mutual gravity. Between the filaments are the voids, vast, nearly empty regions of space that can span hundreds of millions of light years. If you could somehow stand in the center of one, the nearest significant galaxy clusters would be 1 billion light years away. The universe would seem much emptier from that vantage point. We live within this web. Our Milky Way is part of a small gathering called the Local Group, which includes Andromeda, Triangulum, and about 50 smaller galaxies. The Local Group itself is part of the Virgo supercluster, which is a tendril of an even larger supercluster complex called Laniakea, a name that means immeasurable heaven in Hawaiian. This hierarchy of structure, from the local to the unimaginably vast, is shaped primarily by gravity and the invisible scaffold of dark matter. Dark matter is the unseen architect of the cosmos. It makes up about 85% of all matter. It doesn't emit, absorb, or reflect light, but we know it's there because of its gravitational pull. We see its effects in how galaxies rotate, how galaxy clusters hold together, and in the subtle distortions of light from distant objects. In the early universe, dark matter collapsed first, forming the blueprint of the cosmic web. Ordinary matter, the atoms that make up stars and planets, flowed into these dark matter wells, cooling and condensing to form galaxies. Every galaxy we see sits at the heart of a much larger, invisible halo of dark matter. Our ability to count galaxies is entirely dependent on our tools. The Hubble Deep Field was a revolution because it showed us what was hiding in the darkness. But Hubble primarily sees visible and ultraviolet light. For the most distant galaxies, their light has been stretched by the expansion of the universe into the infrared part of the spectrum. To see them, we need a different eye. That eye is the James Webb Space Telescope. With its larger, gold-coated mirrors and instruments tuned to infrared light, Webb can see galaxies Hubble could not. Its first deep field images, released in 2022, revealed galaxies that existed when the universe was only a few 100 million years old. Some were surprisingly bright and mature, challenging our models of how quickly galaxies can form. With every new instrument, we peel back another layer of the unseen. But even Webb has limits. There are galaxies hidden by dust, which absorbs visible light and re-emits it as infrared heat. There are galaxies hidden behind the thick disk of our own Milky Way, in what astronomers call the zone of avoidance. And there are countless dwarf galaxies, so faint they blend into the glow of the night sky itself. The 2 trillion estimate is an attempt using mathematics and physics to account for all these hidden populations, galaxies we cannot yet see but know must be there. Each of these galaxies has its own story, its own character. The Whirlpool Galaxy, with elegant spiral arms tugged by a companion. The Sombrero Galaxy, a gleaming edge-on disk with a dark lane of dust. Centaurus A, a chaotic elliptical galaxy bisected by a dusty belt, evidence of a past collision. The Cartwheel Galaxy, a perfect ring resulting from a smaller galaxy punching through its center. They are not just points in a catalog, they are individual worlds of stars, each with its own history of birth, evolution, and sometimes violent collision. And in all of them, on countless planets orbiting their stars, the same laws of physics and chemistry operate. Carbon forms, water condenses, complexity emerges. This naturally leads to a profound question that haunts every astronomer who considers these numbers. With 2 trillion galaxies, each with billions of stars, and likely even more planets, could life be out there? The numbers suggest it is almost a statistical certainty. Yet we see no evidence, no signals, no visits, no signs of vast engineering projects reshaping solar systems. This is the Fermi paradox, the uncomfortable silence of a universe that should, by all reasonable estimates, be teeming with civilizations. Perhaps life is exceedingly rare. Perhaps intelligent civilization is even rarer. Perhaps civilizations are common but short-lived, destroying themselves or fading back into silence before they can reach out. Or perhaps the distances are so vast that signals and visits are practically impossible. 2 trillion galaxies might as well be infinite if the space between them cannot be crossed. We do not know. The silence of the cosmos is one of its most haunting features. As we look to the future, we see that the number of galaxies is not fixed. It is decreasing. Gravity continues to pull galaxies together, In 4 or 5 billion years, the Milky Way and Andromeda will likely begin a long dance that will end in a merger, forming a single larger elliptical galaxy. Two entries in the cosmic catalog will become one. This process is happening everywhere, throughout the universe. The cosmos is consolidating. On much longer timescales, driven by the accelerating expansion of the universe caused by dark energy, a profound isolation awaits. Distant galaxy clusters will be pushed beyond our cosmic horizon by the expansion of space itself. Their light will fade from view, redshifted into darkness. A civilization in the far future, perhaps living in the merged Milky Way Andromeda galaxy, may look out and see only a handful of nearby galaxies in an otherwise empty sky. They would have no evidence of the vast cosmic web we see today. They might conclude the universe is small and mostly empty. They would be wrong, but they would have no way to know. We live in a privileged time, cosmically speaking, early enough that the universe is still full of light, that the evidence of its history is still visible across billions of light years. We have the tools to see it and the curiosity to try to understand it. That figure, 2 trillion galaxies, is more than a number. It's a measure of our reach. It represents a journey from standing on a planet and looking up at the stars to building instruments that can collect photons that have traveled for over 13 billion years. We cannot truly hold the scale of it in our minds. Our brains didn't evolve to comprehend such numbers. But through mathematics, through engineering, through the slow accumulation of knowledge passed from one generation to the next, we can know it. We can map it. We can trace the structure of the universe across scales that dwarf our existence. The light arriving at telescopes tonight left distant galaxies when Earth was young, when dinosaurs walked, perhaps even before Earth itself existed. In that light is the story of cosmic evolution, written in wavelengths we have learned to decode. The count is not finished. New telescopes, like the European Extremely Large Telescope or the Nancy Grace Roman Space Telescope, will look deeper and fainter. The number may grow again as we discover populations of galaxies we cannot currently detect. Or the number may shrink as we refine our understanding of what constitutes a galaxy, where the boundaries lie between galaxies and star clusters and other cosmic structures. For now, 2 trillion galaxies is our best answer. It's a testament to a universe of overwhelming scale and beautiful structure, to our own persistent effort to see our place within it. The search is not for an end point, but for a clearer view. And with each new view, the universe becomes a little less mysterious and a little more marvelous. Not because we've solved it, but because we've learned enough to ask better questions. 2 trillion galaxies, each one a city of stars, each star potentially surrounded by planets, each planet a world with its own geology, its own chemistry, perhaps even its own story of life. And we, standing on one small world, orbiting one ordinary star in one typical galaxy, have managed to count them all, or at least make our best attempt. That achievement, that audacious effort to map the unmappable and count the uncountable, might be one of the most remarkable things our species has ever done. The universe is vast, but our capacity to comprehend it, to measure it, to wonder at it, that is vast in its own way.